Hi everyone, in this video we are going to see how to make a good guess about the relative position of two circles based on the provided equations of the circles. Let's suppose we have a circle like this and let's suppose we have another circle like this. If the two circles are far apart, then their relative position could be like this. Now if we bring the yellow circle little closer to the green circle, then their relative position could be like this. Here the circles are actually touching each other externally. Now if we push the yellow circle even further towards the left side, then the positions could be like this, where the two circles would be intersecting each other. And then if we push the yellow circle a little further to the left, then their positions could be like this. They could be touching each other internally. And what happens if we push it even further to the left? Well, the relative position could be like this, where the circles don't touch or intersect, however they are not concentric yet. Now I'm going to push it a little further to the left to make them concentric. So this is the concentric position. So as we saw, there are 6 different relative positions possible for two circles, and we're going to go into a little more details about each of the relative positions. Let's talk about the first situation. Here the circles are far apart, they do not touch, they do not intersect. There is a bit of distance between the centers of the circles. Now for this position, how many tangents can we have? Well, we can have two direct common tangents. As you see in the diagram, these are called direct common tangents. And also we can have another type of tangent, and they kind of look like this. They are called the transverse common tangent. So as you can see, we can have actually 4 different common tangents between the two circles. 2 of them are direct common tangents and 2 of them are indirect or transverse common tangents. Now let's take a look at the distance between the centers. If we are provided with the equations of these two circles, from the given equation we should be able to find out the coordinates of the center, and also we should be able to find out the radius of each of the circles. Let's suppose the centers of the circles are C sub 1 and C sub 2, and let's join them with a straight line. From the given equation of the two circles, we should be able to find the coordinates of the center of each of the circles, and then we can calculate the distance between the centers. We can simply use the distance formula to calculate the distance between the centers. Now in this case, let's assume that the radius of the first circle is r sub 1 and the radius of the second circle is r sub 2. And now we are going to look at the distance in terms of the radii of these two circles. So you can say the distance between the two centers would be equal to C sub 1a plus ab plus bc sub 2. Those are the 3 different segments of that line segment between C sub 1 and C sub 2. And we can write it as r sub 1 plus ab plus r sub 2, which can be written as r sub 1 plus r sub 2 plus ab. And from here, if we bring r sub 1 plus r sub 2 to the left hand side, we can say that C sub 1, C sub 2, the distance between the centers, minus r sub 1 plus r sub 2, this quantity is equal to ab. And guess what? AB is nothing but the length of a line segment, which is a positive quantity, right? So we can denote that as greater than 0. So here we are creating an inequality. And from here we can then say that C sub 1, C sub 2 is greater than r sub 1 plus r sub 2. So if you think about two given circles, I mean if the equations of the circles are given, you are able to find out the location of the centers, and using the distance formula you can calculate the distance between the centers, and also from the given equation you can calculate the radius of the circles. And then if you find that the distance between the centers is actually greater than the sum of their radii, then you clearly know that the circles are actually far apart. They do not touch each other externally, they do not intersect each other, they are just far apart if the distance between the centers is greater than the sum of their radii. So just based on the given equations of the circles, you can make a very good guess about their relative position, and depending on the finding, you can also make a good guess as to how many tangents could we have and how they could look like in reality. So for this particular scenario, if the distance between the centers is greater than the sum of their radii, then the circles are far apart and 4 common tangents are possible. 2 of them would be direct common tangents and the other 2 would be transverse common tangents or indirect common tangents. I hope things are clear up to this point. Next, we are going to take a look at the second scenario. In the second scenario, when the circles are touching each other externally, how many common tangents can we have? Well, we can have 2 direct common tangents like this. And can we have any transverse common tangent? Yes, we can have 1 transverse common tangent. In the previous diagram, as you saw, there are 2 transverse common tangents. Now those 2 transverse common tangents will coincide with each other and they will become just 1 transverse common tangent. And that is going to look like this, the blue line here. This is the transverse common tangent. just one of them. So in this particular scenario, there will be 3 common tangents. 2 of them will be direct common tangents and 1 of them would be transverse common tangent. Next, let's study the distance between the centers. Let's suppose the centers are located like this, C sub 1 and C sub 2, and based on the given equations of the circles, we should be able to find the coordinates of the centers, and then using the distance formula, we should be able to calculate the distance between the centers. And also, if we try to express this distance in terms of the radii of these 2 circles, then we can say C sub 1, C sub 2, this distance can be written as C sub 1a plus a C sub 2, and that can be written as r sub 1 plus r sub 2. So for any 2 given circles, if you find that the distance between the centers that you calculate using the coordinates of the centers and the distance formula. So if you find that the distance between the centers is equal to the sum of their radii, then you know that the circles are actually touching each other externally. So based on the distance between the centers and their radii, you can make a clear guess about their relative position. And in this case, if you find that the distance between the centers is equal to the sum of their radii, then obviously the circles touch each other externally. And in that case, there will be 3 common tangents, 2 direct common tangents and 1 transverse common tangent. I hope things are clear up to this point. Next, we are going to study the third relative position between 2 circles. So the third situation is like this, where the circles intersect each other. In this scenario, how many common tangents can we have? Well, we can have 2 direct common tangents like this. Now, can we have any transverse common tangent? The answer is no, because the circles actually they intersect each other. There is no way we can draw a transverse common tangent. However, they are going to have something called a common chord. So let me draw the common chord and then you will see what I am talking about. You see that pink line there that I have drawn between the 2 points of intersection? That would be called a common chord, because if you think about it, it is a chord for the bigger circle. Also, it is a chord for the smaller circle. So it is actually a common chord between the 2 intersecting circles. So for this type of relative position of 2 circles, we can have 2 direct common tangents and a common chord. Now let's study the distance between their centers. Let's suppose the centers are located at C sub 1 and C sub 2, and let's connect the centers by a line segment. Here the distance between the centers will be actually less than the sum of their radii and greater than the difference of their radii. Now in the previous scenario, how you have seen when the circles are touching each other externally, the distance between the centers is actually equal to the sum of the radii. Now here I have pushed the circles a little closer, so the distance between the centers will be little less than the sum of their radii, and also it will be greater than the difference of the radii, which you are going to see in the next scenario. There the circles will be touching each other internally, and you will see that the distance between the center will be actually equal to the difference of the radii. Now for this particular scenario, the one that we are talking about now, the distance between the centers will be like this. It will be less than the sum of their radii but greater than the difference of their radii. So if you are given the equations of 2 circles, and from the given equations you calculate the distance between the centers and also you calculate the radius of each circle, and then if you find that the distance between the centers is actually less than the sum of the radii but greater than the difference of the radii, then you know that the circles are positioned kind of like this. They are intersecting each other, and in that case we can have 2 direct common tangents and a common chord. I hope it is clear. Next, let's move on to the 4th scenario, where the circles will be touching each other internally. When the circles are positioned like this, how many common tangents can we have? Well, from the diagram, I am sure you can make a good guess that there could be only 1 common tangent. And that common tangent could look something like this. It will go through the point of contact for the 2 circles, and the 2 direct common tangents, in this case, they are actually coinciding with each other. So it became just 1 direct common tangent. Can we have any more common tangents? The answer is no, because we cannot draw any other tangents that will be common to both the circles. So now let's study the distance between their centers. Let's suppose the centers are located like this, C sub 1 and C sub 2. C sub 1 is the center of the green circle and C sub 2 is the center of the yellow circle. And let's connect C sub 1 with the point of contact. Now can we say that C sub 1, C sub 2, this distance is equal to C sub 1a minus C sub 2a? That's just pure geometry, and this can be written as R sub 1 minus R sub 2. and I'm using an absolute value sign to make sure that we are getting the positive value here depending on whether r sub 1 is greater than r sub 2 or r sub 2 is greater than r sub 1. So when the circles touch each other internally, the distance between the centers would be like this. So now suppose you have been given the equations of two circles, and based on the equations you derive the coordinates of the centers, and then using the distance formula you calculate the distance between the centers, and also you calculate the radius of each of the circles. And then finally, if you notice something like this, that the distance between the circles is actually equal to the difference of their radii, then you know the circles are actually positioned like this. They are touching each other internally, and in that case we can have only one direct common tangent. I hope it is clear. And next we are going to talk about the fifth scenario, where the smaller circle will be inside the larger circle. In this scenario, can we have any common tangents? The answer is no, because there is no point which is common to both the circles, so we cannot draw any common tangent for these two circles for this particular scenario. Now let's study the distance between the centers. Let's suppose the centers are located like this, and then I have joined the centers and extended the line all the way to the boundary of the larger circle. Now here can we say that the distance between the centers would be c sub 1b minus ab minus c sub 2a, and that can be written as r sub 1 minus ab minus r sub 2, and that can be written like this. And from here, if we bring that r sub 1 minus r sub 2 onto the left hand side, we can write it like this. And if you think about that negative AB is actually the length of a line segment, and negative AB will definitely be less than 0. So we can convert it into an inequality like this. And from here we can say then c sub 1 c sub 2 minus r sub 1 minus r sub 2 is less than 0. And then we can say that c sub 1 c sub 2 is less than r sub 1 minus r sub 2. And to be safe, I am going to use the absolute value sign. So we can say that the distance between the centers will be like this when one circle is inside the other circle. And in this case, there would be no common tangent between the two circles. I hope everything about this scenario is clear. And next we are going to look at the final scenario, which is the sixth scenario, where the two circles could be concentric. So in this scenario, can we have any common tangents? The answer is no, because there are no common points between the two circles. So we cannot draw any tangent that will be common to both the circles. And if the circles are concentric, what would be the location of their centers? Well, the centers will be coinciding with each other. So I have drawn only one point there, but that is the center for both the circles, meaning it's a common center. So the distance between the centers would be actually 0, because it's the same point. So if you are given the equations of two circles, and there you see the centers of the two circles are located at the same point, then you know they are concentric circles. And in that case, there will be no common tangents, and the distance between the centers obviously will be 0. So as you saw, if you are given the equations of two circles, the first thing you should do is you should find the distance between their centers and their radii, and then based on the relationship between the distance of the centers and their radii, you can make a very good guess as to how the circles are positioned relative to each other, whether the circles are far apart, whether the circles are touching each other externally, whether the circles are intersecting each other, whether the circles are touching each other internally, whether the circles don't touch, don't cut, but one circle is inside the other one but not concentric yet, or whether the circles are concentric circles. Next, let's take an example. Suppose we have an example like this that says find the relative positions of these two circles. The equations are given here: x squared plus y squared minus 6x minus 8y minus 11 equals 0. And the equation of the second circle is x squared plus y squared minus 14x plus 6y plus 42 is equal to 0. So from here we have to somehow determine the relative position of these two circles. So let's get started with the solution. Let's identify these two equations as equation number 1 and equation number 2. Also next to them, I am going to write the general form of the equation of a circle. For the first one, I am using g sub 1, f sub 1 and c sub 1. And for the second one, I am using g sub 2, f sub 2 and c sub 2. So now let's compare each of these equations with their general form. For the first one, we can say that 2g sub 1x is equivalent to negative 6x. And from there we can say then g sub 1 is equal to negative 3. And from there we can say negative g sub 1 is equal to positive 3. And similarly, 2 f sub 1 y is equal to negative 8y, and from there f sub 1 is equal to negative 4, and from there negative f sub 1 is equal to positive 4. What about the radius of the first circle? Well, we know the formula for radius, square root of g squared plus f squared minus c. So for the first circle, let's call the radius as r sub 1, and that will be equal to square root of g sub 1 squared plus f sub 1 squared minus c sub 1. Now let's plug in the values of g sub 1, f sub 1 and c sub 1. So the radius of the first circle turns out to be 6 unit. Now let's take a look at the second equation. From the second equation, we can say that 2g sub 2x is equivalent to negative 14x, and from there we can say that g sub 2 is equal to negative 7, and negative g sub 2 will be equal to positive 7. Similarly, 2 f sub 2y is equal to positive 6y, and from there we can say f sub 2 is equal to 3, and negative f sub 2 is equal to negative 3. And let's also calculate the radius of the second circle. R sub 2 is equal to square root of negative 7 whole squared plus 3 squared minus 42, and that is equal to square root of 49 plus 9 minus 42, which is equal to square root of 16, and that is equal to 4. We are going to take the positive value here because we are talking about the radius of a circle. We cannot take the negative value, we should take the positive value. So the radius of the second circle turns out to be 4 unit. So for the first circle, let me make a note of the radius and the coordinates of the center. Radius is 6 unit. Coordinates of the center are 3, 4. Similarly, for the second circle, the radius is equal to 4 unit and location of the center is at 7, negative 3. Next, we are going to calculate the distance between the centers of the two circles, and for that we are going to use the distance formula. So c sub 1, c sub 2, that's the distance between the centers of the two circles, that would be equal to square root of 7 minus 3 whole squared plus negative 3 minus 4 whole squared. That's basically from the distance formula, and if we simplify that, it turns out to be square root of 16 plus 49, and that is equal to square root of 65, which is equal to 8.06, approximately 8.06 unit. Now let's see the sum of the radii. R sub 1 plus R sub 2 is equal to 6 plus 4, that is equal to 10 unit. And also let's see the difference of the radii. R sub 1 minus R sub 2 is equal to 2 unit. And here we can clearly see that 8.06 is actually greater than 2 but less than 10. That means the distance between the centers is actually greater than the difference of the radii but less than the sum of the radii. Earlier in the video we have seen that this is actually the third situation where the two circles intersect each other, and that is when we have seen this property that the distance between the centers is actually greater than the difference of the radii but less than the sum of the radii. So in this case we can conclude that the circles actually intersect each other, and that's the answer for this example. I hope everything made sense. Thank you for watching. See you in the next video.